Howdy, my name is Jason Pavick, and welcome to my thesis presentation on interactive UI design for virtual reality. My thesis artifact is a one-room interior of a near-future space vessel created within Unreal Engine 4.22, intended to be viewed in virtual reality. My specific pillars of focus, mastery, and research are Diegetic User Interface, which focuses mainly on the user's ARM-mounted DataPad and in-scene UI elements, virtual reality, to build a scene for the Oculus Rift headset designed specifically for high-functioning VR and to utilize the unique tools and feedback present in VR experiences. And my third area is Interactables, focusing mainly on my generator interactive machine and also several other in-scene elements. Overview of presentation. What is Diegetic UI? VR design needs, Interactables in VR games, demonstration of project, building the UI and the iterative process of improvement, creating a high-functioning VR scene in Unreal Engine 4, interactable techniques, artifact and design, and lastly, closing statements. What is Diegetic UI? In simple terms, a Diegetic UI exists inside of the same world as the player's character, and both the player and the character perceive information in a similar manner, as opposed to the more common non-diegetic UI, where the player and the character perceive information differently, usually involving what's known as a heads-up display, where 2D graphical information is pinned to specific corners and spaces on the monitor that only the player outside of the game world can see. I have this example of Halo because it actually uses both diegetic and non-diegetic UI elements. I would like to highlight that the ammo counter is both present in the HUD graphic for the player and on the widget of the assault rifle itself for the character to see. Typically, games will go one way or the other, but there is a near limitless realm of possibilities. There is not one exclusive way of doing diegetic UI. As an example of a less common form of diegetic UI, Splinter Cell Conviction projects Sam Fisher's thoughts and memories onto the walls and environments. This both helps the player understand his mental state while also providing tutorials and backstory without forcing the player to slow down or enter menus. In virtual reality, mostly you are looking through the eyes of the character. Having non-diegetic fixed elements to your face is very uncomfortable and can easily break immersion. For that reason, it is important to find a better way of sharing information with the player. I started my project by researching display pads in other VR games. On the top left is a pad from Lone Echo. This one is flashy and sci-fi with its visuals. However, something like this would be too small and confusing to be used practically. On the opposite end of the spectrum, in the bottom image, is the watch-mounted menu from Rec Room. It puts function first. Buttons are very large and easy to touch, and there is no unnecessary visuals to distract the player. For my DataPad, as seen on the right, I wanted to find a happy middle ground. I wanted it to be functional, legible, easy to use, and still have a bit of sci-fi visual flair. Although VR requires a higher than normal amount of pixels to be rendered, the amount of pixels on a visible object or widget is typically significantly lower resolution, which is often referred to as the screen door effect. Because of that, it is important to use larger than normal text of very legible typefaces and to avoid thin lines whenever possible. For interactive menus and other UI elements, the user lacks the typical precision of a mouse, and therefore the designer must avoid clutter and they must appropriately space all interactable elements to avoid overlap and accidental triggering. In the picture is the specific hardware that I have designed my project for. The Oculus Rift S released in May 2019 and is the current flagship headset for the Oculus brand. I've designed my project in a way that should be hardware agnostic, but I can only promise quality performance for the Rift S. The Rift S has a maximum render resolution of 2560 by 1440p at 80 frames per second. It is recommended above all else to keep your frame rate above 70 frames per second, or users will feel motion sickness. Next, you should design your scene with players in mind, meaning you need to give your players enough space to stand and move arms in all directions without clipping through walls and ceilings. Not all players are the same height. Ideally, you want tall players, short players, and players in chairs to be able to play the game in the same way as the others. VR allows players to get as close to your models and props as they want to. For this reason, you will not want to underdeliver on polygon or texture quality, and most props should be watertight. Stereoscopic depth is both a plus and minus in VR. Plus, that depth will enhance immersion by better mimicking real life. Minus, because it makes flaws all the more apparent and makes it more difficult to get away with tricks. On the left is a screenshot from Valve's robot repair portion of the lab. This was the first experience that I had that highlighted the potential and beauty of VR to me in a way that would be near impossible to be replicated with a traditional mouse and keyboard setup on a single monitor experience. However, there are some notable flaws with their demo. Their machine is designed to intentionally confuse the player, and it is literally impossible to solve the puzzle and win. Failure is by design. For my generator, I wanted to create my own similar experience, but I wanted my system to be clear and solvable by the user. In VR, the player uses their own hands to interact with the world. Your hands are your main tools in most VR games, whether it be holding a saber in Beat Saber or repairing health in Half-Life Alyx. This machine from Half-Life Alyx requires you to insert this bug-like cylinder first, and then it stitches health directly into your left hand, as opposed to just pressing X in a normal game and feeling better. In these next slides, I will be showing a demonstration of my artifact through a series of videos. In VR, for my scene in particular, I decided to go with an omnidirectional space to where you can move any direction, look any direction. The user's not forced to look at one thing at any time. The first thing you might notice when looking around and looking at your hands is this big red menu button. This pulls up the DataPad, which provides information about the scene and is the main way that the user will be able to interact with the scene. I have also provided these tooltip elements because while I have given enough information through symbology for users to be able to figure out how to solve my generator problems, some players still prefer having text to guide them, and I felt that was a valid reason of including a text-based solution. Within the DataPad, you may click the same buttons to open up the generator as you would without the DataPad by just clicking on the buttons above the generator. And this first part is opening up the core, which has the red atom. As you can see, the atom exhausted here is red and needs to be replaced. And so you pull it out, and it grows and dissipates and eventually implodes within your hand, leaving nothing behind. And so when you pull it open, it's empty, and you need to grab the clean replacement atom and snap it into place. And after doing so, on your DataPad, it is now a green stable atom. And for the second area, I have this chip, and it was important to me to use symbology to let the player know where this belongs. You see the 3 dots there, lets them know that they can snap it in place. And as seen before, this hexagon exists on relevant areas of the scene. And the 3 dots on the DataPad were 2 green and 1 red because there's one missing one. And snapping that into place, all 3 are green now. And the third area, when you open it up, has these loading widgets, these update widgets. And when you press the button, it loads, it turns from red to yellow, and when it's finished, it turns to blue. Currently, this isn't connected to any other system, but the variables are exposed to in a full-size game. This could be tied to greater systems that track your updates and let you do compound tasks that use your update information throughout. Within the DataPad, I felt it was important to include a radio system because in current space travel, radio is the most important tool for survival, and without it, you will die in space. Information is generally carried over the radio. In mine, the DataPad is more visual, but I feel like in the future, radio's not going to go away. So I came up with this system for a 3-channel radio, and each one has their own audio and their own separate radio wave animations. Iteration is key to designing a functional UI that is as visually pleasing as it is legible. My workflow largely involves these 4 pieces of software. I start in Illustrator with vectors. I rasterize and add additional elements with Photoshop, and any animated elements go through After Effects. And creating cards and geometry for the Diegetic UI are done with 3ds Max, and it makes the job way easier. This is the earliest version of the DataPad, which I was mostly focused on learning what was possible in VR. And some of what I noticed, the lines got easily lost or didn't render at all. Not enough shades of gray makes it hard to contrast and see what's happening. And then small fonts just really do not work. Going forward into the prototype, I made a few changes. I may have actually taken a few steps back here. Building a physical frame around the pad made it feel less open, and it was harder to interact with. Some of the line work is more visible, but the text is very difficult to read. The textures themselves often feel blurry and slow to render. Lastly, it feels completely flat, which by no means takes advantage of what VR has to offer. So I made some pretty radical redesigns and changes in vertical slice. Of the major changes, the DataPad is much larger and with easier to press buttons, and it's easier to read the text. The depth and curve has been added, which in a headset adds much to the stereoscopic depth and feels better. And I focused on minimalist design aesthetics as well as putting function first, meaning I was avoiding filler elements, and everything on the DataPad should relate back to actual scene elements. And moving forward into the spring semester, I made a few more changes, but I tried to keep the most of the design from the vertical slice version. I added a background grid, which helps show a lot of the depth versus the previous when it was just blue. Rotating the DataPad didn't give you any change, but having the grid helps that. I worked on improving the symbolism, and all of these icons relate back to the scene itself, and they have meaning and helps the player figure out where they should go. I added drop shadows in corners and on the text to improve legibility. And in multiple ways, I optimized the performance by reducing cost of certain textures and materials, and also reducing my reliance on things like the event tick and other costly updates. On the left, you can see the buttons outside of the generator from my vertical slice milestone. This was the first time that I had made the connection that the scene and the DataPad itself were one and the same, and should constantly relate back to each other. On the right is a tooltip element that I came up with because symbols aren't always enough for everyone, and some people prefer having text to guide them to where they should go, so I felt that was a valid option. For any tiling elements, such as this hexagonal grid, breaking the image down into its simplest tile improves both the visual fidelity and performance by needing fewer dedicated pixels. To generate single image sprite sheets from image sequences, I use a free piece of software called Blueit. It is important to know that the differences between visible, hidden, collapsed, hit test invisible, and self hit test invisible. Most new users will only want to use visible and hidden states for the UI, but that is actually a very bad practice. Visible is shown on screen and is clickable. Collapsed is not shown and does not receive information from update events. Hidden is not shown, but it still continues to receive information from the updated events. Hit test invisible is shown on screen but is not clickable, and self hit test invisible is shown on screen and acts as a parent to a nested child widget that has clickable elements. Returning back to VR, it is critically important to do your research and learn the best practices before trying to build your project blindly. Starting with the VR template from Unreal Engine is a good start in that it helps provide useful scripts in the headset script, movement script, and hand interaction scripts. However, it is far from properly optimized, and if unchanged, will cause issues further down the lines of development. From the beginning, I would suggest choosing between forward rendering and deferred rendering. The main difference between the two is when and how the lighting is calculated. Forward renders light directly to the pixels at an early stage and will provide quicker performance. Deferred will render light later in separate passes, which is more costly, but it provides better appearance of reflections, transparencies, shadows, and VFX. Unreal defaults to deferred rendering, however both Epic and Oculus suggest using forward rendering in VR projects. I initially actually stuck with deferred rendering because I knew that my scene was going to be heavy in transparency, VFX, and reflections. I thought that the visual fidelity would outweigh the performance benefits of forward rendering. I was wrong. After switching, I was able to adjust the textures to look nearly identical to the previous deferred look using tools like the high quality reflections material node and enabling the VR MSAA anti-aliasing to reduce the jaggedness. The performance improvements are significant. As pictured, the atom from the generator core here appears visually about the same between the deferred and forward milestones, but the performance view, this alpha one has lots of red high cost materials versus the beta milestone. The only thing that changed was switching to forward rendering, and now everything is green and easy to render. For performance reasons alone, I would highly recommend switching to forward rendering for VR projects. In developing VR assets, traditional low poly modeling with baked normals may not cut it. In large part, I went with a mid poly modeling workflow without normal maps. For mid poly, you want to model in the large details and smooth the corners by using chamfers and face weighted normals. Now, the reason that I am not relying on normal maps is the technology limitations in perception. Normal maps provide an illusion between the camera and the object face and provides additional depth. In a two-camera stereoscopic VR setup, this illusion is broken here by being able to see around the intended angle of the normal map projection. Face normals are the direction that each triangle sees as being outward. Correctly seeing this will make smooth geometry without the need for normal maps. While it can be done manually by hand, the improved face-weighted normal script for 3ds Max can do this accurately for you in a very short amount of time. You will only know your true performance once the game has been packaged. Checking Start in VR and enabling the HMD in your level script will ensure that your game launches to the headset. Again, research, iterate, improve, and repeat. For the generator handle to function correctly, I went with a system of locational references. There is more than one plausible solution to this problem, but in my solution, the parts of the generator reference both each other and the player's hand to know where to be and where to stop at all times. A system of triggers determines if and when parts can move. Most of these interactive elements have more than one way that they could have been solved. For my chip and atom core, I came up with the idea that there should be an invisible version already in place and a version in the scene that you can pick up. The chip becomes invisible. The invisible chip becomes visible once the held chip is placed into this collision box. This destroys the more costly chip that's being held in hand and enables the visibility of the chip in place. This ensures both reliability that things will be in place 100% of the times playing, and it will no longer receive the unnecessary calculations which could help improve your scene performance. From the beginning, it is a good idea to set up a game mode blueprint to act as a repository for your various scene variables that will affect more than one object. This is both easier and provides better performance than casting the same information from one blueprint to another, and down the chain. Another way of optimizing your interactions is to limit your use of event tick. Event tick is an action that happens every rendered frame, so in my case, 80 times per second. This is costly. Instead, when possible, you should use a timer event that lets you specify how often to update. This varies from item to item, but can provide very noticeable improvements in the scene. In the alpha milestone, I radically changed my scene's art style to be more interesting and more in line with how I see near future design. I based my look heavily on praised Neo-Deco design principles. Neo-Deco is a bridge between Art Deco and the 1960s space race movement, but still with near future aspects. It utilizes earthly elements like woods and leathers to cover surfaces. There's gold brass trim in geometric patterns, which is very common in the Art Deco design movement. Functional structural elements still use steel, and future tech has elements of glass, emissive lights, and aluminum. And by beta, this is how my scene looked. I also improved my sky by using a free piece of software called Spacescape. Spacescape is a free piece of software for developing generative space cube maps. What went well? Legible UI throughout the scene, performs very well in VR, all of the systems work and communicate with each other in real time, unique and interesting sense of style. What went wrong? The desire for unnecessary features. Overdraw and the performance-related issues persisted during multiple milestones of the development cycle. Tunnel vision on small things when big things needed to be addressed. Drastic style redesigns fairly often, and inefficient code during early chunks of the dev cycle. Be even better if plan better, test more, research so much more, especially in the case of VR optimizations. Kill your babies, which means make cuts early, make cuts often, or find the project down to its bare essentials. And to take more time to learn scripts and proper interactive workflow before going at it. How this helps future cohorts? They will know some effective methods and pipelines for developing a user interface. I've picked up several VR tricks that I would have loved to have known about when I began this project. If I had 6 more months, additional pages and functionality to the DataPad menu. I would add additional rooms that serve a different purpose. I would have additional interactive systems that exist within those new rooms. I will have modeled and textured hands, and I would have created scripts that limit hands and heads from going through walls and floors, etc. And I would work on improving existing scripts. Thank you very much for listening today.